Look up at the night sky, and you might think we've got it all figured out: planets orbiting the sun, moons drifting through space, the occasional comet streaking by. But what if I told you our solar system is hiding secrets so strange, so baffling, that even the brightest minds can't explain them? We live in a cosmic neighborhood bursting with mysteries, from eerie lights on distant worlds to objects that defy the laws of physics. And here's the wildest part: the more we explore, the more questions we uncover. Think about it. We've sent probes to the outer edges of our solar system, landed rovers on Mars, and peered into the depths of space with telescopes powerful enough to spot a speck of dust 1,000,000 miles away. Yet, despite all that technology, the universe keeps throwing us curveballs. There are storms on Jupiter that rage for centuries, moons with underground oceans that might harbor life, and bizarre, unexplained signals that seem to come from nowhere. These aren't just quirks, they're full-blown enigmas that challenge everything we thought we knew. So what's really out there? That's exactly what we're diving into today. We're counting down 25 of the most mind-bending, spine-tingling mysteries our solar system has to offer. Some might make you question reality. Others could hint at possibilities we've never even dreamed of. And by the end of this journey, you'll see our cosmic backyard in a whole new light, not just as a collection of rocks and gas, but as a place where the impossible might just be waiting to be discovered. Ready to unravel the secrets? Let's begin. Imagine if everything in the universe, every star, every galaxy, was being silently pulled toward some invisible force beyond the edges of what we can see. That's the spine-chilling mystery astronomers call the dark flow. It's as if the cosmos has a secret current, tugging entire clusters of galaxies in one unified direction like leaves caught in a cosmic river. And here's what makes it so unsettling. According to everything we know about gravity, this shouldn't be happening. The dark flow was first spotted when scientists studied the movement of galaxy clusters using the cosmic microwave background, the faint afterglow of the Big Bang. They expected to see random motion, the usual push and pull of gravity between nearby objects, but instead they found something bizarre. Hundreds of galaxy clusters were all streaming toward the same patch of space at staggering speeds, like moths drawn to a flame we can't see. So what's pulling them? One theory suggests the answer lies beyond the observable universe. Maybe there's a massive structure, a supercluster of unimaginable size, exerting gravity from so far away that its light hasn't had time to reach us yet. Or perhaps it's evidence of another universe brushing against ours, its gravity leaking through like a shadow from another dimension. Some even speculated could be a remnant of the chaotic forces at play during the Big Bang itself, a cosmic fingerprint we're only now beginning to decipher. Whatever the cause, the dark flow reminds us just how little we know. Even with our most advanced telescopes, we're still peering through a keyhole into the vast unknown. And if something out there can move galaxies like chess pieces, what else is lurking beyond the edges of our sight? Now picture this. It's a quiet summer night in Ohio, 1977. A radio telescope known as the Big Ear is silently scanning the cosmos, listening for whispers from the stars. Then, out of nowhere, a signal erupts from the speakers, so powerful, so unnatural, that the astronomer reviewing the data circles it in red ink and scribbles one word in the margin: wow. This wasn't just static or some earthly interference. The signal came from the direction of the constellation Sagittarius, blasting at a frequency scientists had long suspected aliens might use if they were trying to communicate. 1420 megahertz, a radio wave that slips easily through the noise of space. For 72 dizzying seconds, it blared louder than anything in the cosmos, should then vanished without a trace. Decades later, we still have no idea what caused it. Teams have scoured that patch of sky for repeats, using telescopes far more advanced than the Big Ear, and yet silence. The wow signal remains a ghost in the machine, too precise to dismiss as natural phenomena. too fleeting to confirm as extraterrestrial. Could it have been a passing comet reflecting radio waves in just the right way, a glitch in our own equipment, or, as some dare to wonder, was it the first and only time we overheard another civilization calling out into the dark? Here's what chills scientists the most: if it was a message, we missed our chance to reply. By the time those radio waves reached Earth, whatever sent them had already been waiting for 1,200 years. And if the sender was listening for a response, well, our own signals wouldn't reach them until the 37th century. One thing's certain: in a universe full of cosmic static, that one burst of noise still echoes as the loudest what-if in history. Saturn's North Pole looks like something straight out of a science fiction novel, a swirling, six-sided storm so precise it could have been drawn with a cosmic protractor. This isn't some blurry, shapeless weather system like the hurricanes we're used to on Earth. No, this is a hexagon, a nearly perfect one, stretching 20,000 miles across, with sides longer than the entire diameter of our planet. And the strangest part, it's been spinning there, unchanging, for at least 40 years. When the Voyager probes first glimpsed it in the 1980s, scientists assumed it was some fleeting anomaly. But when Cassini arrived decades later, the hexagon was still there, its razor-sharp edges defying everything we know about fluid dynamics. Storms don't behave like this. On Earth, turbulence breaks structures apart, yet Saturn's hexagon persists like a celestial tattoo, with winds screaming at 300 miles per hour along its edges. So how does a storm, a chaotic, turbulent force of nature, hold such a rigid geometric shape? Some theories suggest it's a standing wave pattern, a kind of atmospheric resonance where swirling gases lock in to a stable form. Others point to deep-rooted jet streams acting like invisible walls, shepherding the chaos into order. There's even speculation that the hexagon might be a towering stack of layered storms, each influencing the one above it like a colossal, spinning honeycomb. But here's what keeps researchers up at night. We've never seen anything like this elsewhere in the solar system. Not on Jupiter with its great red spot, not on Neptune with its supersonic winds. Saturn's hexagon is utterly unique, a puzzle wrapped in a mystery, spinning silently in the darkness of space. And until we send another mission to peer beneath its swirling clouds, this six-sided enigma will remain one of the solar system's most mesmerizing secrets. Early morning on June 30th, 1908, in a remote stretch of Siberian wilderness, the sky split open. Witnesses described a fireball brighter than the sun streaking across the horizon, followed by a blast so powerful it knocked people off their feet 40 miles away. When the dust settled, 800 square miles of forest lay flattened, millions of trees scorched and uprooted in an eerie radial pattern, like matchsticks scattered by a giant's hand. Yet when scientists rushed to the site, they found no crater, no smoking gun, just silence and a mystery that would haunt us for over a century: the Tunguska Event. At first, everyone assumed it was a meteorite impact, but the lack of any crater or fragments defied logic. The force was estimated at 10 to 15 megatons, 1,000 times more powerful than the atomic bomb dropped on Hiroshima, yet nothing solid seemed to have struck the ground. Some theorized the object disintegrated miles above the Earth, its shockwave acting like an invisible hammer slamming into the forest. Others proposed wilder ideas: a chunk of antimatter annihilating itself in our atmosphere, or even a miniature black hole passing through the planet. One of the most compelling modern explanations suggests it was a comet, a massive ball of ice and dust that vaporized completely before hitting the surface, leaving no trace but devastation. But here's where it gets stranger. Decades later, studies of the soil revealed microscopic mineral spheres rich in iridium and nickel, elements common in asteroids. Tree rings from the area show evidence of a radioactive surge, as if the blast carried some form of cosmic energy we still don't fully understand. And then there are the eyewitness accounts. nomadic reindeer herders spoke of sky spirits unleashing fire, while distant villages reported nights so bright you could read a newspaper outdoors at midnight. The Tunguska Event remains a cosmic detective story with no final answer. It happened once, violently and without warning, leaving behind a puzzle that challenges our understanding of near-Earth threats. If a similar explosion occurred today over a major city, the consequences would be catastrophic. Yet despite advances in astronomy, we still can't predict or fully explain what tore through Siberia that summer morning. Was it a warning shot from the universe, a freak accident in the chaos of space? One thing's certain until we uncover the truth: Tunguska stands as a humbling reminder of how vulnerable we are to the unknown. Among all the oddities in our solar system, the Moon hides one of the most baffling scientific contradictions. It once had a magnetic field. That might not sound shocking at first. Earth has one, Jupiter has a monstrously strong one, but here's the catch. Planetary magnetism requires a churning, molten core, and the Moon is too small to have maintained that kind of internal heat for long. Yet lunar rocks brought back by Apollo astronauts tell a different story. They're magnetized, locked in time with evidence of a magnetic field that shouldn't have existed. Think of Earth's magnetic field like an invisible force field, generated by our planet's swirling liquid iron core. The bigger the world, the longer it stays hot enough to keep that dynamo running. Mars, for example, lost its magnetic field billions of years ago as its core cooled. But the Moon, it's a fraction of Earth size, so small that even if it started with a molten core, it should have frozen solid within a few 100 million years. And yet, those Apollo rocks suggest its magnetic field clung on for at least 1 billion years. That's like expecting a campfire to burn for decades after you've kicked dirt over it. So how did the Moon pull it off? One radical theory suggests it wasn't alone. Early in its history, the Moon might have been tidally locked in a gravitational dance with Earth, its core constantly flexed and heated by our planet's pull like a ball of clay being squeezed. Another idea points to massive asteroid impacts, collisions so violent they temporarily liquefied the Moon's interior, jump-starting its magnetic engine. There's even a wilder possibility that the Moon's core wasn't made of pure iron but something exotic, an alloy with properties we haven't yet discovered. But here's what makes this mystery so urgent. If we've misunderstood how small worlds generate magnetism, it could rewrite the rules for exoplanets too. Imagine finding an Earth-sized world orbiting another star, only to realize it can't sustain a magnetic field the way we predicted. Or worse, what if we've underestimated the potential for life on tiny moons, assuming their cores went cold too soon? The Moon's magnetic past isn't just a cosmic curiosity. It's a glaring gap in our understanding of how worlds big and small come alive. And until we send more missions to drill deeper into its secrets, this lunar paradox will keep scientists staring at the sky, wondering what else they've gotten wrong. In 1976, NASA Viking 1 orbiter snapped a photograph that would ignite decades of conspiracy theories. A mile-long formation on the surface of Mars that eerily resembled a human face. Staring blankly toward the sky with shadowed eyes and a pronounced nose, it looked like something sculpted by an ancient civilization. The image spread like wildfire, fueling speculation that Mars might have once harbored intelligent life, or worse, that someone didn't want us looking too closely. But here's where reality steps in. When higher-resolution cameras like those on the Mars Global Surveyor revisited the site in the late 1990s, the so-called face crumbled into what it always was, a weathered mesa, its human-like features nothing more than a trick of light and angle. The same way clouds can form shapes of animals or a slice of toast might seem to bear the Virgin Mary's likeness, our brains are wired to seek patterns, especially familiar ones. Scientists call this pareidolia, the tendency to impose meaning on random shapes, and Mars' rocky surface is a Rorschach test for the imagination, yet the legend never truly died. Even after NASA debunking, the face on Mars took on a second life in books, films, and late-night radio shows. Why? Because it taps into something deeper than facts, our hunger for mystery, the thrill of feeling like we're on the verge of uncovering something monumental. It's the same reason we still debate crop circles or Bermuda Triangle disappearances long after explanations exist. The unknown is irresistible, and let's be honest, Mars hasn't made it easy to let go. Over the years, rover photos have captured alien skulls, spoon-shaped rocks, even what looked like a thigh bone, each one a new flare-up of cosmic pareidolia. The face was just the first spark, the one that taught us how eagerly we'll project our myths onto the red planet. Maybe that's the real lesson here. Space isn't just a place we explore with telescopes and rovers. It's a canvas for our hopes, our fears, and the stories we can't stop telling about what or who might be waiting out there. Venus is a planet of extremes, a scorching, toxic world where lead would melt on the surface and the air crushes with 90 times the pressure of Earth. But beneath its suffocating clouds lies a mystery even more bizarre. Its atmosphere is racing around the planet at hurricane speeds while the surface below barely moves. Imagine a marathon runner sprinting circles around someone standing still, and you've got Venus superrotation, a phenomenon so extreme, it defies every model scientists have thrown at it. Here's how weird this gets. Venus takes 243 Earth days to complete one rotation, slower than any other planet, making its day longer than its year. But up in the clouds, the atmosphere screams around the globe at 220 miles per hour, completing a full lap every 4 days. That's 60 times faster than the planet itself spins. To put that in perspective, if Earth's atmosphere moved like that, a jet stream could carry you from New York to London in under 2 hours without the ground below you budging an inch. So what's whipping Venus skies into such frenzy? The short answer, nobody knows for sure. Early theories pointed to thermal tides, sunlight heating the atmosphere and creating pressure waves that push it forward. Others suggested turbulence or friction between cloud layers might act like a cosmic accelerator. But when scientists tried simulating these ideas in climate models, everything fell apart. The numbers refused to spit out winds this fast. Even the most advanced supercomputers couldn't replicate the relentless speed of Venus' atmospheric carousel. Then came the curveball. In 2021, Japan's Akatsuki orbiter spotted something even stranger. Giant gravity waves rippling through the planet's clouds, stretching for thousands of miles like wrinkles on a spinning top. Some researchers think these waves might be transferring energy from the lower atmosphere upward, acting like an invisible hand cranking the winds faster. Others argue Venus' thick, sulfuric acid clouds could be absorbing sunlight unevenly, creating a feedback loop of heat and motion. But here's the real kicker. Superrotation isn't just a Venus quirk, it's a cosmic anomaly. We've seen hints of it on Saturn's moon Titan and a few exoplanets, but nowhere as violently persistent. And that's what keeps scientists up at night. If we can't explain the mechanics on a planet right next door, how can we trust our models for worlds light years away? Venus isn't just a cautionary tale about runaway greenhouse effects. It's a rotating, raging classroom where the universe is teaching us just how much we still don't understand about the dance of wind and world. Beyond the orbit of Neptune, the solar system doesn't just fade quietly into the void. Instead, it's bustling with a vast ring of icy worlds known as the Kuiper belt, home to Pluto, Haumea, and countless other frozen relics from the dawn of our cosmic neighborhood. But something strange happens about 4.5 billion miles from the Sun. The belt doesn't taper off gradually like you'd expect. Instead, it slams into an invisible wall, a boundary astronomers call the Kuiper Cliff, where the number of objects drops off so abruptly it's as if someone took a cosmic eraser to the outer solar system. This isn't just a gentle decline. At around 50 astronomical units, 50 times Earth's distance from the Sun, the population of Kuiper Belt objects plummets by a staggering 99%. One moment, you've got a celestial highway packed with icy bodies, the next near silence, and that kind of sharp edge doesn't occur naturally. In a system shaped by gravity and chance, you'd expect a gradual thinning like sand fading into ocean waves. Instead, the Kuiper Belt looks like it was carved with a knife. So what or who could have done this? One spine-tingling theory points to an unseen planet lurking in the darkness. Dubbed Planet 9 by researchers, this hypothetical world could be 10 times the mass of Earth, orbiting so far out that it's remained invisible to our telescopes. Its gravity might have shepherded the Kuiper Belt's outer objects into clustered orbits while flinging others into oblivion, leaving behind this stark divide. Others suggest something even more violent, a close encounter with a rogue star in the solar system's infancy, a gravitational intruder that ripped away the outer debris like a thief in the night. But here's the twist: the Kuiper Cliff isn't just a curiosity, it's a clue. If Planet 9 exists, its influence could explain other solar system oddities, like the peculiar orbits of distant objects like Sedna, which loop around the Sun in paths nothing else can account for. Yet after years of searching, we've found no direct evidence of this phantom world. That leaves us with two equally unsettling possibilities. Either our detection methods are missing something massive in our own backyard, or the Kuiper Cliff is the scar of a cataclysmic event we can't even imagine. Until we send probes beyond Pluto or finally spot that elusive ninth planet, this frozen frontier will keep its secrets. But one thing's certain: the abrupt edge of the Kuiper Belt isn't just a boundary. It's a cosmic crime scene, and we're still piecing together what happened. In the vast emptiness of space, where even the slightest miscalculation can send missions wildly off course, NASA Pioneer probes did something inexplicable. As they hurtled toward the edges of the solar system, scientists noticed a tiny but persistent tug, slowing them down just a fraction more than physics predicted. At first, it seemed like a glitch, but when both Pioneer 10 and 11 exhibited the same unexplained deceleration, it became impossible to ignore. Dubbed the Pioneer Anomaly, this microscopic deviation sent shockwaves through the scientific community, sparking debates that would last decades. Was it a flaw in our understanding of gravity, a hidden force acting on the probes, or something even stranger? The numbers were maddeningly precise. Each year, the Pioneers fell behind their projected trajectories by about 300 miles, equivalent to losing a single second every decade on a cross-country road trip. Tiny, yes, but in the unforgiving precision of orbital mechanics, utterly significant. Teams combed through decades of telemetry data, checking for mundane explanations: fuel leaks, thruster misfires, even the faint pressure of sunlight pushing against the spacecraft. Nothing added up. The anomaly persisted like a ghost in the machine, whispering that somewhere our models were wrong. Then came the wild theories. Some physicists suggested this was evidence of dark matter clinging to the solar system, its invisible mass subtly altering the probe's path. Others proposed modifications to Einstein's theory of general relativity, arguing that gravity might behave differently over vast interstellar distances. The most tantalizing and controversial idea was that the anomaly revealed a previously unknown force, a fifth fundamental interaction lurking in the cosmos. For a time, it seemed the pioneers might have stumbled upon physics' next great revolution, but science has a way of humbling even the boldest speculations. Years later, meticulous analysis pinpointed a far more mundane culprit: heat. Not from the sun or cosmic rays, but from the probes themselves. Pioneer's nuclear power sources emitted warmth, and as that thermal radiation bounced off the spacecraft's uneven surfaces, it created a faint but constant push, like a car idling just enough to slow its own momentum. When researchers finally modeled this effect in 2012, most of the anomaly vanished. Case closed, not quite. even after accounting for thermal recoil, a whisper of the anomaly remains, a discrepancy too small to dismiss entirely. Some argue it's residual error, while others wonder if there's still a deeper truth hiding in the data. The pioneers, now silent and drifting toward the stars, continue to carry that mystery with them. And perhaps that's the real lesson here, not just about heat or gravity, but about how even the tiniest inconsistencies can lead us to question everything we think we know. The universe loves to surprise us, often in ways so subtle we almost miss them entirely. Mars should be a dead planet when it comes to methane, a gas that sunlight and chemical reactions should break apart within a few hundred years. So why does NASA Curiosity rover keep sniffing out sudden, mysterious bursts of it in the Martian air? These aren't faint traces either. Some spikes hit concentrations 10 times higher than the baseline, appearing unpredictably like puffs of smoke from an invisible source, then vanishing without a trace. For scientists, this isn't just a curiosity. It's a full-blown enigma with two equally thrilling possibilities. Either Mars is hiding active geology we've never seen before, or something alive is quietly exhaling beneath the rust-colored soil. Let's start with the non-living explanation. On Earth, methane often leaks from volcanoes or seeps up through cracks in tectonic plates. But Mars hasn't had confirmed volcanic activity for millions of years, and its crust isn't shifting like ours. Unless, and here's the twist, there's a hidden heat source deep underground, perhaps pockets of magma still simmering far below the surface, releasing methane through fissures we can't yet detect. There's another geological culprit, a process called serpentinization, where water and certain minerals react under pressure to produce methane. If liquid water exists in Mars' subsurface, as some evidence suggests, this chemical factory could be churning out the gas in sporadic bursts. But then there's the electrifying alternative, biology. On our planet, over 90% of atmospheric methane comes from living organisms, from microbes in swamps to the digestive tracts of cows. If Martian microbes exist or existed recently, they could be producing methane in isolated pockets, perhaps beneath ice sheets where liquid water lingers. The spikes might be their fleeting signatures, escaping when permafrost cracks or dust devils stir the surface. It's a tantalizing thought, but here's the catch. Without catching a microbe red-handed, we can't rule out non-living sources. Even more frustrating, the European Space Agency's Trace Gas Orbiter, designed specifically to study Martian methane from orbit, keeps reporting no detections at all, creating a baffling discrepancy with Curiosity's ground-level measurements. This contradiction deepens the mystery. Could methane be pooling near the surface in localized patches too small for orbiters to spot, like invisible geysers only a rover driving past would notice? Or is something destroying the gas faster than we've calculated, scrubbing it from the atmosphere before satellites can see it? Every new dataset seems to add another layer of questions. What makes these methane spikes so thrilling isn't just the hunt for their source. It's the realization that Mars isn't the static, fossilized world we once assumed. Something is stirring, whether it's the slow grind of rocks reacting underground or just maybe the faint breath of life clinging on in the shadows. Until we sink drills into the Martian soil or catch a whiff of organic molecules alongside the methane, this puzzle will keep scientists and dreamers alike staring at the red planet, wondering what secrets it's still holding close. Most dying stars fade away in a chaotic blaze of gas and dust, their final breath scattering into space like smoke in the wind. But one, HD 44179, did something different. Instead of erupting into a typical, wispy planetary nebula, it wrapped itself in a glowing, crimson structure so precise it looks crafted by cosmic architects, the red rectangle. This isn't your average stellar farewell. Named for its striking shape when first glimpsed through ground-based telescopes, the red rectangle is anything but simple. High-resolution images reveal an intricate latticework of luminous crossbars and concentric rings like a celestial honeycomb or the beams of an alien cathedral. At its heart, two cones of dust and gas stretch outward, their edges so sharply defined they seem carved with a laser, and that deep red hue, it's not just for show. The nebula's unique chemistry scatters light in a way scientists rarely see, infused with complex organic molecules that shouldn't survive this close to a dying star's radiation. So how does a star, in its death throes, create such geometric perfection? The leading theory points to a binary system, two stars locked in a gravitational waltz at the nebula's core. As one star shed its outer layers, the other's orbit could have funneled the ejector into those precise conical shapes, sculpting chaos into symmetry. Think of it like spinning a garden hose. The water doesn't spray randomly but spirals into a neat, predictable pattern. Only here, the hose is a star's dying breath, and the force shaping it is an invisible dance between two cosmic partners. But even that explanation leaves gaps. Why the vivid red glow, so unlike the blues and greens of most nebulae? The answer might lie in a type of carbon-rich molecule called polycyclic aromatic hydrocarbons, essentially soot. These compounds, often found in comet dust or candle flames, are thriving in the red rectangle, fluorescing under ultraviolet light like neon signs in a stellar graveyard. Yet their presence is baffling. These molecules are fragile. The intense radiation from the central star should have torn them apart eons ago, raising the question, what's replenishing them? Then there's the X-shaped structure. While binary stars can explain the cones, those crossbars defied models until researchers proposed an even wilder idea: a thick disk of dust girdling the stars like a hula hoop. As material escapes along the star's poles, the disk's edges could be casting shadows in the outflowing gas, creating the illusion of intersecting beams. It's a cosmic magic trick, one that requires nearly perfect alignment for us to see it head-on. The red rectangle isn't just a pretty oddity, it's a laboratory for processes we've never witnessed elsewhere. Those organic molecules, they're the same building blocks that on Earth might have seeded life. The precision of its structure, a rare glimpse into how binary systems can choreograph even the messiest stellar deaths. And the deeper we look, the more questions arise. Are there other similar nebulae we've missed because their angles hide their geometry? Could this teach us how dying stars distribute complex chemistry across the galaxy? For now, the red rectangle keeps its secrets, glowing defiantly against the blackness of space, a reminder that even in death, the universe has a flair for the dramatic. And as telescopes grow sharper, who knows what other impossible shapes we'll find etched in the skies? In October 2017, astronomers spotted something streaking through our solar system that shattered all expectations, an object unlike anything we'd seen before. Named Oumuamua, Hawaiian for scout or messenger from afar, this strange cigar-shaped visitor wasn't just the first confirmed interstellar traveler passing through our cosmic neighborhood. It was breaking the rules. As telescopes tracked its trajectory, scientists noticed something impossible to ignore. Oumuamua wasn't coasting under gravity alone. It was accelerating as if pushed by some unseen force. At first, the explanation seemed straightforward. When comets speed up, it's usually due to outgassing sunlight heating their icy surfaces, releasing jets of vapor that act like natural thrusters. But Oumuamua showed no visible coma, the glowing halo of gas and dust typical of comets. No tail, no debris, just a faint reddish hue and that inexplicable boost in speed. Researchers scrambled to model how outgassing could occur without leaving a trace, suggesting maybe it vented pure hydrogen or other hard-to-detect molecules. But even those theories felt like forcing a square peg into a round hole. Then came the fireworks. Harvard astrophysicist Avi Loeb floated a controversial idea. What if Oumuamua wasn't a natural object at all? What if its acceleration was caused by light pressure? An artificial sail, perhaps designed by an intelligent civilization. The internet erupted. Suddenly, Oumuamua became a Rorschach test for how far we're willing to stretch our imaginations. Was it a fragment of alien technology, a derelict probe, or just an oddly shaped rock with quirks we didn't yet understand? The truth is, Oumuamua's mystery cuts deeper than speculation about extraterrestrials. Its very existence hints at a cosmos teeming with interstellar nomads, drifting between stars in numbers we've barely begun to estimate. Since its discovery, we've spotted more of these visitors, like the comet Borisov in 2019. But none have behaved like Oumuamua. Its dry, rocky composition defied expectations for icy interstellar objects, and that nagging acceleration still lacks a satisfying explanation. Perhaps the most unsettling possibility isn't that Oumuamua was alien tech, but that it revealed a gap in our cosmic vocabulary, a natural phenomenon we've never encountered before. Could there be a new class of objects that accelerate without visible outgassing? Some researchers propose exotic ices we've yet to study, or even porous, lightweight materials that react unpredictably to sunlight. Others wonder if tidal forces from a long-ago stellar encounter stretched Oumuamua into its odd shape while altering its internal chemistry, leaving it primed for bizarre behavior. One thing's certain, Oumuamua's fleeting visit, it's now beyond Pluto, never to return, left us with more questions than answers. Whether it was a cosmic coincidence or something more deliberate, this silent scout from the stars challenged our assumptions in ways we're still grappling with. And as future telescopes scan the skies for more interstellar interlopers, we'll be watching closely, ready for the next strange traveler that might rewrite the rules all over again. Jupiter's poles are chaos frozen into perfect symmetry, where storms don't just rage but arrange themselves with eerie geometric precision. At the North Pole, 8 cyclones spin around a central vortex like petals on a nightmarish flower. The South Pole, 6 storms locked in a hexagonal formation, each larger than the continental United States. These aren't transient squalls. They've maintained their shapes for years, defying every rule we know about how turbulence should behave. On a planet where winds scream at 300 miles per hour and atmospheric pressures crush probes like soda cans, these polygonal hurricanes shouldn't exist. Yet there they are, spinning in lockstep like cogs in a cosmic clock. What keeps these cyclones from merging or flying apart? Earth's hurricanes dissolve when they collide, their energy dissipating into the surrounding chaos. But Jupiter's polar storms do the impossible. They bump shoulders without collapsing, their boundaries holding firm even as they whirl at breakneck speeds. The answer might lie beneath the visible cloud tops. Some scientists suspect vast, rotating jets act like invisible fences, corralling the cyclones into position through sheer momentum. Others propose that the storm's roots dig deep into Jupiter's interior, tapping into heat rising from the planet's core, a hidden energy source fueling their unnatural stamina. Then there's the polygonal puzzle. Why 8 in the north, 6 in the south? Laboratory experiments with spinning fluids can create similar shapes, but only under tightly controlled conditions that don't mirror Jupiter's violent atmosphere. One theory suggests the number of cyclones depends on how much energy flows upward from Jupiter's depths, with different latitudes channeling that power into distinct geometric patterns. It's as if the planet has a hidden atmospheric code, a mathematical rulebook we're only beginning to decipher. Every new image from NASA, a Juno spacecraft, deepens the mystery. Infrared scans reveal the polar cyclones are warmer at their tops and colder at their bases, the opposite of Earth storms. Their cores are studded with towering thunderheads, yet their edges remain razor-sharp, like someone drew them with a protractor. And while their outer winds rage, their centers are eerily calm, not empty eyes, but dense, swirling mazes of cloud layers stacked like pancakes. This isn't just a lesson in planetary weather. It's a masterclass in how little we understand fluid dynamics at scale. If Jupiter can sustain these perfect storm polygons for years, what other atmospheric magic tricks are hiding across the cosmos? Until we send probes brave enough to dive beneath those churning clouds, these cyclones will keep spinning silent, stable, and utterly inexplicable. When NASA Lunar Reconnaissance Orbiter began mapping the Moon's gravity field in exquisite detail, scientists expected to find subtle variations, gentle dips and swells like those on Earth. Instead, they discovered something far stranger: massive, invisible lumps of gravity scattered across the lunar surface, tugging on spacecraft with unpredictable force. These aren't just minor fluctuations, they're gravitational anomalies so intense they've sent orbiting probes wobbling like drunk drivers, fighting to stay on course. Welcome to the bizarre world of mascons, short for mass concentrations, one of the Moon's best-kept secrets and a navigational nightmare for missions daring to skim its surface. Mascons don't play by the rules. On Earth, gravity is relatively smooth because our planet's mass is evenly distributed beneath its crust, but the Moon, it's riddled with hidden gravitational potholes, most lurking beneath its largest impact basins. Crash a spacecraft into orbit over the Imbrium Basin or the Sea of Serenity, and it'll suddenly lurch forward or drop altitude without warning, yanked by an unseen force. During the Apollo missions, these anomalies were so disruptive that navigators had to manually tweak trajectories mid-flight, compensating for tugs they couldn't fully explain. So what's causing these hidden heavy spots? The leading theory points to ancient asteroids' cataclysmic impacts so violent they punched through the Moon's thin crust, unleashing floods of dense mantle material that pooled beneath the surface like syrup settling in a bowl. Over time, these molten blobs cooled and solidified, leaving behind dense, concentrated lumps of iron-rich rock that pull harder than their surroundings. Imagine a lead weight sewn into a foam mattress. That's essentially what mascons are, invisible anchors warping the Moon's gravitational fabric, but mysteries remain. Why haven't these dense patches relaxed over billions of years, smoothing out like spilled honey? The Moon lacks Earth's tectonic activity to churn and redistribute its innards, but even so, gravity should have evened things out more than this. Some researchers speculate the mascons might be encased in rigid, unmoving layers like fossils trapped in lunar amber, while others wonder if the Moon's unique crustal properties somehow lock them in place. Then there's the puzzle of their longevity. Mascons shouldn't just sit there undisturbed. Micrometeorite bombardments, moonquakes, even the tidal flexing from Earth's gravity should have scrambled them long ago. Yet they persist, defying erosion in a way that suggests the Moon's interior is far more rigid or far stranger than we've assumed. The practical implications are just as wild. Future lunar bases or mining operations will need mascon maps as essential as topographic charts, lest their drones or rovers get yanked off course by invisible pitfalls. And for scientists, these anomalies are time capsules, clues to the Moon's violent infancy, when asteroids rained down and sculpted its face in ways we're only beginning to grasp. But perhaps the most humbling lesson lies in what mascons reveal about our cosmic backyard. Even the Moon, our closest celestial neighbor and the only world humanity has walked upon, still guards secrets that defy expectation. If something as fundamental as gravity can hide such surprises here, what other invisible oddities are waiting to be uncovered, not just on the Moon, but on every world we've yet to explore? Deep in the direction of the constellations Hydra and Centaurus, something monstrous is pulling at our galaxy and everything around us with irresistible force. Astronomers call it the Great Attractor, a gravitational anomaly so powerful it's yanking entire galaxies toward it at speeds exceeding 14 million miles per hour. But here's the frustrating part: we can't see it. Lurking behind the dense star clouds and dust lanes of the Milky Way's galactic plane, this cosmic heavyweight hides in what's ominously dubbed the zone of avoidance, a region so obscured by our own galaxy's glare that traditional telescopes peer right through it like fogged-up glasses. The story of the Great Attractor reads like a detective novel where the culprit leaves gravity as its only calling card. Scientists first noticed its pull in the 1970s when mapping the motion of galaxies. Instead of drifting apart evenly with the universe's expansion, thousands of galaxies, including our own, were all streaming toward the same mysterious point. The math was undeniable. Something with the mass of tens of thousands of Milky Ways was out there, bending the paths of galaxies like a hidden hand guiding marbles across a table. But figuring out what's causing this gravitational tug of war is like solving a puzzle with half the pieces missing. X-ray and radio telescopes have pierced some of the obscuring dust, revealing a sprawling cluster of galaxies called the Norma cluster near the heart of the Great Attractor. Yet even this massive structure doesn't fully account for the staggering pull we're observing. That's led to spine-tingling suggestions. Perhaps the Great Attractor is just the tip of something far larger, like the edge of a supercluster we've barely begun to map, one that could rewrite our understanding of cosmic structure. Then there's the elephant in the room, dark flow, the mysterious motion of galaxy clusters beyond the Great Attractor's reach. Some researchers wonder if this isn't just a local anomaly but part of a chain reaction stretching billions of light years, with the attractor itself being pulled toward something even more immense. It's a Russian nesting doll of gravitational mysteries, each layer revealing a deeper enigma. The Great Attractor forces us to confront a humbling truth. Even as we map the cosmos with unprecedented precision, our own galaxy's bulk shields us from seeing one of the most influential forces in our intergalactic neighborhood. Until next-generation telescopes or space-based observatories crack the zone of avoidance's veil, this gravitational phantom will keep pulling the strings silent, unseen, and utterly in control. Among the countless craters pockmarking the dwarf planet Ceres, one stands out like a cosmic beacon. Ocata crater, home to the most puzzling geological feature in the asteroid belt, a cluster of radiant bright spots gleaming against the dark, rocky surface. These aren't subtle reflections, they're blindingly bright patches, some dazzling 10 times more intensely than their surroundings, as if someone scattered shards of polished glass across the crater floor. When NASA Dawn spacecraft first captured them in 2015, scientists were floored. A dwarf planet barely 600 miles wide shouldn't have such dramatic, concentrated brightness. Yet here they were, defying expectations and sparking debates that still rage today. At first glance, the leading explanation seems straightforward enough. Spectral analysis reveals these spots are mostly sodium carbonate, a salt compound common in Earth's evaporative environments like dried-up lake beds. On Ceres, scientists think these deposits formed when briny water seeped up from underground reservoirs, erupting onto the surface in icy geysers or cryovolcanoes before evaporating under the weak sunlight, leaving behind shimmering salt crusts. Think of it like the white residue on your skin after swimming in the ocean, only on a planetary scale. But here's the twist: this process shouldn't be happening today. Ceres is geologically stagnant, its internal heat long since faded. So how did these deposits stay so glaringly fresh? That's where the mystery deepens. Some of these bright areas show signs of recent activity, features that look like frost or haze hovering above the surface, as if volatile materials are still sublimating into the thin atmosphere. One particularly luminous spot, called Cerealia Facula, sits atop a dome-like structure, suggesting pressurized brine might have oozed upward like toothpaste from a tube. If that's true, Ceres could be hiding a layer of liquid or slushy brine deep below its crust, occasionally punching through when impacts fracture the surface. But maintaining that kind of hidden reservoir for billions of years would require an unforeseen heat source, possibly from radioactive decay or tidal forces, challenging our assumptions about how small, icy worlds behave. Then there's the question of timing. Ocata crater is relatively young, just 20 million years old, a blink in cosmic terms. So did the bright spots form in a single, catastrophic event when the crater was born? or have they been renewing themselves in fits and starts ever since? The answer could rewrite what we know about dwarf planets. If Ceres is still geologically alive, it joins an exclusive club of active small worlds like Europa and Enceladus, places where internal heat and liquid water might create niches for extraterrestrial life. But perhaps the most tantalizing clue lies in the spot's uneven distribution. They're not scattered randomly but clustered in Ocata's central pits and fractures, as if the impact that carved the crater unlocked pathways for briny upwellings. Similar bright deposits have been spotted in a handful of other Ceres craters, but none as vivid or concentrated. This selectivity hints at something special about Ocata. Maybe a particularly rich salt reservoir beneath it, or a unique impact angle that triggered deeper upheaval. The more we study these gleaming anomalies, the more they seem like cosmic road signs pointing to larger truths. If tiny Ceres can harbor briny eruptions and hidden liquids, how many other small worlds might be doing the same? Could salt deposits like these preserve organic molecules or even microbial fingerprints in their crystalline structures? For now, Ocata's bright spots keep their secrets, shining silently in the darkness, a glittering enigma reminding us that even the smallest bodies in our solar system can hold the biggest surprises. On Neptune, where the sun is little more than a faint star, logic says the poles should be the coldest places on the planet, shrouded in perpetual twilight and starved of solar warmth. Yet when astronomers trained infrared telescopes on this icy giant, they stumbled onto a thermal paradox. Neptune's south pole isn't just warmer than expected. It's roasting, glowing at temperatures hundreds of degrees hotter than anywhere else on the planet while bathed in the weakest sunlight of all. It's like finding a scorching desert at the heart of an ice sheet, a defiance of physics so glaring it rewrites the rules for how planetary atmospheres behave. The numbers are baffling. Neptune's average temperature hovers around -350 degrees Fahrenheit, cold enough to freeze hydrogen. But at the South Pole, thermometers spike by a staggering 60 degrees. That doesn't sound like much until you realize Neptune's atmosphere shouldn't have localized heat spikes at all. Unlike Earth, where seasons and sunlight drive temperature swings, Neptune's weak solar energy gets diluted across a turbulent, ultra-cold atmosphere 50 times thicker than ours. Heat should diffuse evenly, not pool at the poles like water in a bowl. So what's cooking Neptune's south pole? The answer might lie in the planet's lopsided seasons. Neptune takes 165 Earth years to orbit the Sun, meaning each season drags on for decades. When Voyager 2 flew past in 1989, the South Pole was tilted toward the Sun, basking in a summer that had lasted since the 1960s. Scientists suspect this prolonged exposure, even to feeble sunlight, triggered a slow-burning atmospheric chain reaction. Ultraviolet light breaking apart methane high in the atmosphere could have created dark, heat-absorbing hydrocarbons, while swirling storms funneled warm gases poleward like a cosmic conveyor belt. But here's the twist: that sunlight explanation only goes so far. Even at peak summer, Neptune's poles receive just 1/900th the solar energy Earth does, nowhere near enough to account for the extreme heating. That's led researchers to probe deeper, literally. Neptune's core might be leaking heat from its formation 4.5 billion years ago, simmering like a dying ember. If that internal warmth rises unevenly, it could surge toward the poles through gaps in the planet's magnetic field, supercharging the atmospheric churn. Or perhaps the key lies in Neptune's supersonic winds, which rip around the planet at 1,300 miles per hour, fast enough to drag heat from lower latitudes and dump it at the poles through sheer momentum. The latest clues come from subtle shifts in Neptune's infrared glow. As the seasons slowly turn, the thermal hotspot is beginning to fade, suggesting sunlight played at least some role. Yet the lingering warmth defies models, hinting at processes we've yet to understand. It's a reminder that even in the outer solar system, where cold and dark reign supreme, nature finds ways to surprise us. And until we send another probe to plunge through Neptune's sapphire clouds, this thermal enigma will keep burning, a silent challenge to everything we think we know about the hidden fires of ice giants. 4.5 billion years ago, when Earth was just a newborn world, our sun shone with only 70% of its current brightness, a faint, cool glow that should have left our planet locked in permanent ice from pole to pole. And yet, geological evidence tells a different story. Ancient rocks show liquid water existed as far back as 4.4 billion years, with signs of rivers, oceans, and even life emerging not long after. This contradiction, a warm, watery Earth under a dim young sun, is one of cosmology's most enduring puzzles, known as the faint young sun paradox. If the math says early Earth should have been a snowball, why wasn't it? The most popular explanation points to Earth's primordial atmosphere as a cosmic thermostat. Today, greenhouse gases like carbon dioxide and methane trap just enough heat to keep our climate stable. But back then, scientists suspect these gases might have blanketed the planet in concentrations hundreds of times thicker than modern levels. Picture an atmospheric pressure cooker, a dense, swirling mix of carbon dioxide, water vapor, and perhaps ammonia, all working overtime to absorb every precious photon from that weak young sun. There's evidence to back this up. Banded iron formations and other ancient minerals suggest Earth's early air was starved of oxygen but rich in chemicals that supercharge the greenhouse effect. But here's where the plot thickens. Greenhouse gases alone might not solve the paradox. Climate models show even a massive CO2 blanket would struggle to compensate for the sun's faintness, especially since higher carbon levels would also trigger chemical reactions with rocks and rainwater, gradually scrubbing the gas from the atmosphere. That's led researchers to propose wilder additives to the mix. One theory suggests methane, a far more potent greenhouse gas, might have been belched out by early microbes, stitching together a thermal quilt woven by life itself. Others speculate Earth's rotation played a role. Days were shorter back then, with the planet spinning like a top in just 6 hours. Faster rotation could have reshaped cloud cover or ocean currents, redistributing heat in ways we're only beginning to model. Then there's the celestial wild card, Earth's orbit. Modern climate assumes a stable, nearly circular path around the sun. But in the chaos of the early solar system, gravitational tugs from Jupiter or passing stars might have stretched Earth's orbit into an oval, swinging us closer to the sun for critical stretches. Even a slight boost in proximity could have delivered enough extra warmth to tip the scales. Or consider Earth's original color. Before plants greened the continents, our planet might have been darker, covered in basalt plains or iron-rich oceans that absorbed sunlight more efficiently, like asphalt soaking up summer heat. The paradox takes an even stranger turn when we compare Earth to its siblings. Venus, despite being closer to the sun, shows no signs of early freezing, likely thanks to its thick, suffocating atmosphere. But Mars, which should have been warmer under the faint sun too, bears clear glacial scars from its youth. Why did Earth thread the needle so perfectly? Some astrobiologists think life might be the missing variable. The earliest microbes thriving in hydrothermal vents could have actively regulated atmospheric chemistry, creating feedback loops that stabilized temperatures. It's a provocative idea that life didn't just adapt to Earth's climate, it might have helped invent it. Ultimately, the faint young sun paradox isn't just about our past. It's a mirror held up to exoplanet science. If we've misjudged how Earth stayed warm, how many habitable worlds might we be overlooking in distant systems? And as our own sun continues to brighten, dooming Earth to eventual overheating, this ancient balancing act offers a sobering lesson. Our planet's climate has always been a high-wire walk between ice and fire, with or without us. The real mystery isn't just how early Earth survived, it's how long our luck will hold. In 1766, a German astronomer named Johann Titius noticed something peculiar about the spacing of planets, a numerical pattern so simple yet so precise, it seemed to whisper of cosmic design. The sequence, later popularized by Johann Bode, became known as the Titius-Bode law, and it claimed to predict the positions of planets with uncanny accuracy. Start with 0, add 4, then double the previous number each step, 0.4, 0.7, 1.0, 1.6, and so on. Assign these numbers as astronomical units the distance from Earth to the Sun, and voila, Mercury, Venus, Earth, Mars, and the asteroid belt all fell neatly into place. Even Uranus, discovered later, aligned with the pattern as if following a script, but here's where the mystery deepens. The law worked flawlessly until it didn't. Neptune and Pluto refused to conform, their orbits deviating wildly from the predicted values. And while the asteroid belt fit the sequence, it wasn't a planet at all but a fragmented debris field. So is this pattern a fundamental rule of planetary formation, or just a cosmic coincidence? One camp argues the Titius-Bode law reflects real physics, a resonance left over from the early solar system's swirling protoplanetary disk. As planets formed, their gravitational tugs might have pushed and pulled material into these predictable zones, like ripples in a pond settling into regular intervals. Simulations of exoplanet systems show similar spacing in some cases, hinting at universal forces at play. Others dismiss it as numerology, a happy accident with no deeper meaning. After all, with infinite possible formulas, some are bound to fit purely by chance. Yet the law's partial success keeps haunting astronomers. What if it's not all or nothing? Perhaps it captures a tendency rather than a strict rule, a shadow of order in the chaos of planetary migration. The debate rages on, a tantalizing reminder that even the simplest patterns in space can hold the most elusive truth. Pluto might look like a frozen wasteland drifting silently in the outer darkness, but beneath its icy exterior lies something astonishing, a beating heart. The vast pearly white expanse known as Sputnik Planitia, a sprawling nitrogen glacier the size of Texas, isn't just a static feature. It's the engine powering Pluto's unexpected weather systems, driving winds across an atmosphere so thin it shouldn't even exist. And if that weren't strange enough, this icy heart might have flipped the entire dwarf planet upside down. When NASA's New Horizons spacecraft zipped past Pluto in 2015, it revealed Sputnik Planitia in stunning detail, a smooth, luminous basin resembling a cosmic valentine. But this heart isn't just for show. Composed mostly of frozen nitrogen with traces of methane and carbon monoxide, the glacier acts like a colossal atmospheric pump. During Pluto's long, slow day equivalent to 6.5 Earth days, sunlight warms the nitrogen ice, causing it to sublimate directly into gas. This vapor rises, creating a temporary, wispy atmosphere. Then, as the sun sets, the gas refreezes, snowing back onto the surface in an endless cycle of evaporation and condensation. Here's where things get wild. This constant sublimation and freezing doesn't just create a thin atmosphere, it generates wind. As nitrogen gas escapes the glacier's western edge, it triggers breezes blowing opposite to Pluto's rotation, sculpting the landscape in ways scientists never predicted. New Horizons captured evidence of these winds in the form of dark streaks and dunes, proof that even in the deep freeze of the Kuiper Belt, weather leaves its mark. But the real shocker, Sputnik Planitia's influence might go far beyond weather. This glacier is so massive and so dense that researchers believe it could have literally tipped Pluto on its side. Imagine spinning a basketball with a lump of clay stuck to one side. Over time, the extra weight would shift the ball's rotation until the clay settles at the equator. That's what scientists think happened to Pluto. Sputnik Planitia's sheer bulk, combined with the relentless addition of fresh nitrogen snow, may have caused the dwarf planet to reorient itself, bringing the glacier to its current position near the equator. The implications are staggering. If true, it means Pluto's geography isn't just shaped by random impacts or geology. It's dictated by the slow, rhythmic heartbeat of an icy clock. And this isn't just some ancient relic. The glacier is still active today, its nitrogen ice flowing like syrup in slow motion, filling in craters and smoothing the surface over millions of years. Why does this matter? Because Pluto was supposed to be a dead world, a frozen fossil from the solar system's birth. Instead, it's a dynamic, ever-changing place where ice dances, winds whisper, and an entire planet might have rolled over to make room for its beating heart. It's a reminder that even in the farthest reaches of our cosmic neighborhood, nature keeps surprising us with its creativity. And if something as small and distant as Pluto can defy expectations, what other secrets are waiting to be uncovered in the dark? On a clear, moonless night far from city lights, if you gaze toward the horizon just before dawn or after dusk, you might catch an eerie, pyramid-shaped glow stretching upward along the path of the sun and planets. This ghostly radiance, known as the zodiacal light, has puzzled skywatchers for centuries. Once thought to be celestial fires or atmospheric anomalies, we now know it's sunlight scattering off countless dust particles drifting through the inner solar system. But here's the unsettling part. There's far more dust out there than comets and asteroids could possibly account for. The numbers don't add up. Every year, Jupiter's gravity flings about 20,000 tons of comet debris into the inner solar system, while asteroid collisions add another 2,000 tons of pulverized rock. Yet to maintain the zodiacal light's brilliance, scientists estimate we'd need a continuous supply closer to 100,000 tons annually. That's 5 times more material than known sources, provide a glaring discrepancy that's had astronomers scratching their heads for decades. One theory points to a hidden population of dark comets. Unlike their icy cousins that blaze spectacular tails, these stealthy objects could be nearly depleted of volatile gases, venting invisible jets of dust as they quietly disintegrate near the sun. Recent surveys have indeed spotted strange, asteroid-like bodies with comet-like orbits, suggesting a previously overlooked class of solar system vagabonds. But even if they exist, could there really be enough to explain the missing dust? Another possibility is far more dramatic, a cosmic demolition derby happening just out of sight. Beyond Mars, the main asteroid belt is littered with fragile, rubble-pile asteroids, loose collections of boulders held together by weak gravity. Computer simulations show these could be grinding themselves to dust through constant low-speed collisions, like sandpaper wearing down wood. Each impact might be too subtle to spot from Earth, but collectively they could be spewing enough fine debris to feed the zodiacal glow. Then there's the wild card, interstellar interlopers. With modern telescopes revealing more visitors like Oumuamua and Borisov passing through our solar system, it's possible a steady rain of tiny interstellar dust grains, each smaller than a grain of sand, could be mixing with homegrown debris. These cosmic hitchhikers would be impossible to track individually, but their cumulative effect might tip the scales. But perhaps the most intriguing clue comes from the dust itself. Spacecraft like NASA Juno probe have sampled the zodiacal cloud directly, finding an unexpected abundance of fluffy, porous particles, the kind that shouldn't survive long under the sun's relentless radiation. Their delicate structure suggests they're being replenished constantly, perhaps from a source we've yet to identify. Some researchers even speculate about dust geysers on distant asteroids, where electrostatic forces or buried ice could be launching fresh material into space like cosmic fountains. The zodiacal light isn't just a pretty glow. It's a forensic snapshot of violence and renewal in our solar system. Every photon we see represents a speck of dust with a story, a comet's final sigh, an asteroid's slow motion crash, or perhaps something even more exotic. And until we account for every last grain, this gentle radiance will keep shining a light on just how much we have left to discover in our own cosmic backyard. The sun's surface simmers at a toasty 10,000 degrees Fahrenheit, hot enough to vaporize rock, but surprisingly cool compared to the inferno raging just above it. Extend your gaze past the photosphere into the wispy outer atmosphere, and temperatures skyrocket to millions of degrees in a layer called the corona. This is the ultimate cosmic contradiction. How can the sun's atmosphere be hundreds of times hotter than its surface, like a roaring campfire surrounded by an invisible, searing heat wave stretching into space? For decades, this puzzle, dubbed the coronal heating problem, has left physicists scrambling for answers. Common sense says heat should diminish as you move away from a source, not explode exponentially. Imagine holding your hand over a stove and feeling more intense heat the farther you pull back. That's the baffling reality of the solar corona, and solving it requires rewriting the rules of how energy travels through star stuff. One leading theory points to nanoflares, countless microscopic explosions peppering the sun's atmosphere like popcorn kernels popping in ultra-slow motion. Unlike massive solar flares that light up headlines, these tiny bursts each release a billionth of the energy but occur relentlessly, everywhere, all at once. Picture the corona as a vast field of magnetic dynamite, with twisted field lines snapping and reconnecting in minuscule but violent bursts, channeling energy outward. If even a fraction of these nanoflares exist, they could collectively pump enough heat into the corona to explain its scorching temperatures, but there's a catch. While satellites like NASA's Solar Dynamics Observatory have glimpsed telltale signs of these nanoflares, brief X-ray flickers too small to resolve directly. No one's been able to confirm they're numerous enough to solve the puzzle. That's led researchers to another electrifying possibility: magnetic waves rippling through the sun's plasma like cosmic guitar strings. The sun's churning interior generates these waves, which race upward along magnetic field lines, carrying energy like vibrations traveling through a rope. When they hit the lower density corona, theory suggests they break, dumping their energy as heat, like ocean waves cresting and crashing onto a beach. The truth might be messier and more fascinating than either idea alone. Recent observations from the Parker Solar Probe, which flies closer to the sun than any spacecraft before it, reveal a corona buzzing with both nanoflare-like activity and turbulent magnetic waves. Perhaps it's not a choice between the two, but a chaotic collaboration. Magnetic waves could prime the atmosphere, creating unstable conditions where nanoflares ignite, turning the corona into a pressure cooker of competing heating mechanisms. What makes this mystery so urgent isn't just academic curiosity. The corona's behavior drives solar wind, shapes space weather, and occasionally hurls planet-shaking storms toward Earth. Understanding its heat could unlock better predictions for disruptive solar flares or even inspire new ways to harness fusion energy. And beyond our own star, this puzzle echoes across the universe. Countless other stars exhibit the same coronal heating, meaning we're grappling with a universal quirk of stellar physics. For now, the sun guards its secrets well, its corona shimmering like a mirage of molten platinum. But with every daring spacecraft dive and high-resolution telescope peek, we're inching closer to unraveling why the star we think we know best still has the power to surprise us. Deep in the periodic table of cosmic mysteries, one element refuses to follow the script: lithium, the lightest metal in the universe. According to our best models of the Big Bang, the fiery birth of everything should have forged precise amounts of hydrogen, helium, and a dash of lithium. But when astronomers tally up the lithium in stars and gas clouds today, something's off. The universe is missing about 2/3 of its expected lithium, a discrepancy so glaring it threatens to crack the foundations of cosmology itself. Here's why this matters. In the first 20 minutes after the Big Bang, protons and neutrons fused in a process called nucleosynthesis, creating the universe's first atomic nuclei. The math predicts that for every 10 billion hydrogen atoms, there should be around 10 atoms of lithium-7. Yet when we look at the oldest stars in our galaxy, the ones that formed from nearly pristine Big Bang material, they show only 3 lithium atoms where there should be 10. It's like baking a cake following a recipe exactly, only to open the oven and find a third of the ingredients vanished without a trace. The hunt for explanations has taken scientists down some fascinating rabbit holes. One leading theory points the finger at stars themselves. As stars age, their churning interiors might destroy lithium by dragging it down to scorching depths where nuclear reactions break it apart. Picture a cosmic recycling plant where lithium atoms get shredded into helium. But here's the problem: even accounting for this stellar digestion, the numbers still don't add up. Some primordial lithium must have disappeared before these stars were born. That's led to wilder possibilities. Could exotic particles from the early universe, like hypothetical actions or other dark matter candidates, have absorbed or transformed lithium in ways we haven't accounted for? Or might the Big Bang's nuclear reactions have unfolded differently than we've simulated, perhaps due to pockets of uneven temperature or density in the infant cosmos? The most radical suggestion is that our understanding of gravity itself might need tweaking at those extreme energies, altering how nuclei fused in those first critical moments. But the plot thickens when we look beyond old stars. The interstellar medium, the gas floating between stars, also shows a lithium shortfall, ruling out stellar destruction as the sole culprit. Even more puzzling, younger stars often have more lithium than their ancient counterparts, as if the universe has been quietly producing fresh lithium in cosmic forges we've yet to identify. Supernova, cosmic rays slamming into atoms, even the winds from red giant stars, all have been proposed as secret lithium factories, but none fully close the gap. This isn't just academic bean counting. Lithium sits at the crossroads of particle physics, astrophysics, and cosmology. If our models can't explain its absence, what else might we be getting wrong about the universe's first moments? The mystery has grown so vexing that some researchers have begun questioning whether we're misinterpreting the data entirely. Could our measurements of ancient stars be skewed by hidden atmospheric effects or unaccounted for chemical mixing? For now, the missing lithium remains a ghost in the equations, a silent reminder that even our most cherished theories are works in progress. Every time we measure the skies, the universe whispers back with puzzles designed to keep us humble. And until we crack this one, that absent lithium will linger like a cosmic riddle waiting for its solution. The story of the Black Knight satellite reads like a sci-fi thriller ripped straight from the Cold War era, a shadowy object allegedly orbiting Earth, whispered to be an ancient alien probe watching us for millennia. Conspiracy theorists claim it predates human spaceflight, pointing to odd radio signals and grainy photos as proof of extraterrestrial surveillance. But peel back the layers of myth, and you'll find a far more fascinating tale of human imagination colliding with real cosmic clutter. This legend took flight in 1954 when newspapers reported that the U.S. Air Force had detected a mysterious satellite in polar orbit years before Sputnik's launch. Theories spiraled. Was it a relic from Atlantis, a spy device from a rival superpower? The intrigue deepened in 1960 when Time magazine mentioned an unidentified object dubbed the Black Knight, fueling speculation it wasn't just space junk but something far more sinister. Fast forward to the internet age, and the myth snowballed, with enthusiasts stitching together a footage of floating debris into a narrative of a 10,000-year-old alien sentinel. Here's the twist: every piece of evidence crumbles under scrutiny. Those ancient radio signals, they matched perfectly with a NASA experiment in 1998 where astronauts tossed a thermal blanket during a spacewalk, a mundane piece of insulation tumbling harmlessly in orbit. The mysterious photos, most were mislabeled shots of discarded rocket parts or the International Space Station's modular segments catching sunlight at odd angles. Even the original 1954 reports, They were likely misinterpreted tracking data from early radar tests or high-altitude balloons, commonplace tech for the time, wrapped in Cold War secrecy. Yet the Black Knight's persistence reveals something deeper than just mistaken identity. This myth thrives because it taps into our primal fascination with hidden watchers and cosmic mysteries. The vastness of space feels emptier if it's just us, so we populate it with legends, turning orbital debris into artifacts of alien intelligence. And in a way, the truth is just as compelling. Earth's orbit is littered with relics of our own making: dead satellites, spent rocket stages, even a lost glove from a spacewalk. These fragments form a museum of human ambition, drifting silently above us. What began as a mix-up in the tense paranoia of the space race has become a cultural touchstone, a reminder of how easily the unknown can spark our wildest stories. The real Black Knight isn't an alien observer, it's us, projecting our hopes and fears onto the endless black, and perhaps that's the most human mystery of all. After exploring 24 of the solar system's strangest enigmas, from rogue planets pulling galaxies to methane whispers on Mars, we're left staring into the night sky with one haunting question: where is everybody? This is the Fermi paradox, the glaring contradiction between the universe's vast potential for life and the eerie silence that greets us. Given the billions of stars, the trillions of planets, and the mind-boggling stretches of cosmic time, the Milky Way should be buzzing with civilizations. Yet all our telescopes and radio dishes here is static. Take just our solar system as Exhibit A. We've got moons with subsurface oceans, planets that might harbor microbial life, and chemistry ripe for biology. If even our modest corner of the galaxy hints at habitability, why haven't we stumbled upon ruins, signals, or visitors? One unsettling answer is that something stops life from reaching the stars, a great filter that could lurk in our past or future. Maybe simple life sprouts easily, but intelligence is a fluke. Or perhaps every advanced civilization inevitably self-destructs, leaving behind radioactive fossils. But there are darker possibilities. Imagine a universe where predators lurk, advanced species that silence rivals before they become threats. Or maybe we're searching all wrong, like ants scanning for smoke signals while aliens communicate via quantum entanglement. Some argue we're just early, born in a cosmic spring before life blooms elsewhere. Others suggest we're the equivalent of an isolated tribe, hidden in a galactic rainforest too vast for others to notice. Yet the most humbling thought, the paradox might not exist at all. Life could be rarer than we think, or so alien we fail to recognize it, those Martian methane spikes. They could be microbes, Europa's ocean, a biological oasis. The truth may be hiding in plain sight, waiting for us to ask better questions. Until then, the silence isn't just a mystery, it's a mirror, reflecting how much we still don't know about our place in the cosmos. From hexagonal storms on Saturn to the eerie whispers of Martian methane, the solar system keeps proving it's far stranger than we ever imagined. Each of these mysteries isn't just a cosmic riddle, it's a crack in the foundation of what we think we know, an invitation to question everything. Take Neptune's inexplicably hot pole, or the way Oumuamua defied physics as it raced past the sun. These aren't just quirks, they're glaring reminders that the universe operates on rules we're still deciphering. What makes these puzzles so thrilling isn't just their strangeness, it's how they push science forward. Every time a probe like Juno or New Horizons beams back data that contradicts our textbooks, it forces us to scrap old theories and dream up new ones. The Pioneer anomaly, it taught us how even the tiniest oversight like heat radiating from a spacecraft's electronics can rewrite our understanding of gravity. The missing lithium in ancient stars, a cosmic accountant's nightmare that might upend our entire timeline of the Big Bang. These aren't setbacks, they're stepping stones, each one dragging us closer to truths we can't yet fathom. And let's not forget the human side of this quest. Behind every cryptic signal or inexplicable storm, there are researchers burning the midnight oil, chasing answers with equal parts frustration and wonder. The Tunguska Event still sparks debates over coffee in conference halls. The WOW signal keeps astronomers tweaking radio telescopes, hoping to catch another whisper from the void. Even the zodiacal light, that soft glow we once took for granted, has teams scrambling to account for missing tons of interstellar dust. Science thrives on these gaps, these nagging questions that refuse to let us settle. So here's the real magic. The solar system's greatest gift might not be the answers, but the mysteries themselves. They're what keep us looking up, launching probes, and building ever sharper telescopes. Because every time we think we've got it all figured out, the cosmos throws another curveball, a hexagon where there should be chaos, a glacier that breathes, a planet that flips itself upside down. These aren't flaws in nature's design. They're the universe winking at us, daring us to dig deeper. The next great discovery isn't just waiting in some far-off galaxy. It could be hiding in plain sight, tucked in the data of a decades-old mission, or shimmering in the faint light of a distant moon. So stay curious, keep questioning. Because the day we stop being baffled by the solar system is the day we stop truly exploring it. And if history's taught us anything, it's that the wildest truths are always lurking just beyond the edge of what we think we know.